so this one is on refactoring, and it is going to be making use of several of the topics that we have so far covered. Oh, let me start my timer. Okay, here we go. Okay, so first of all, what do we mean by refactoring, and what is the general definition of refactoring? So refactoring is a disciplined technique for restructuring a body of code that you want to alter in some way. You want to either you want to restructure it. You basically want to change its internal structure without necessarily changing its external behavior. Now, in our context, it doesn't always apply exactly this, because we also sometimes do refactoring to change the behavior. So I would reword this a little bit in the context of scientific software as altering its internal structure with constrained changes in its external behavior, constrained and known changes in the external behavior. This is fundamentally different from development because we are not starting from scratch. We already have a working code that people are using and therefore have opinions about how much you can disrupt. But because the code is a working code, you sort of know and understand the behavior. So there is less of unknowns in there. And you always can build enough baselines before you start mucking around with the code so that you can use those for comparison. So you're not basically working in the dark, as may happen in a code that you're starting from scratch. So there can be many reasons why you may want to undertake refactoring. One of the most common ones in scientific software is that you start out with a spaghetti code and you want to turn it into a much more manageable modular code so that its sustainability is improved. You could be doing a refactoring because you started out with a code that was, again, a spaghetti code, but you were fine with it because you understood everywhere where the potential pitfalls were there in the code and you need to avoid them. But now that you're ready to release it to the outside users, you don't want the code to be in that state. You want the code to be much easier to use and understand. And so you may want to refactor it for that purpose. Very often, a very frequent occurrence in high performance computing area is that platforms change. And till today, it hasn't been true in my experience that a new platform comes along, even if it is supposed to resemble the previous platforms. The kind of, in extreme computing, which is what this particular training program is dedicated for, there are enough changes that no platform behaves like previous platforms completely. And so there is a need to refactor the code to make it ready for the new platforms. And finally, it may be because you want to expand the capabilities. So add more physics, add more solvers, or you want to increase the structural flexibility in order to be able to expand those capabilities. So you could be refactoring for any of these reasons. Okay, so this time around, I'm going to, before I go much deeper into ways of doing refactoring, I want to go back to our running example. And I want to refer you to the repository that the hands-on repository that we have. So we are back to that heat example. And in the repository, there are two versions. One of them is a single file with a monolithic code, which is what would be a typical spaghetti code would look like. The other one is a modularized, reusable, and maintainable code. So an exercise that you may want to do on your own as a part of getting your hands dirty with refactoring options is to assume that you only have the first version, and then you would do the refactoring to get to the second version. So before we start to do that kind of refactoring, and I'm actually not going to do walk through this particular example of refactoring. I will walk through a much smaller and much more limited in scope refactoring example during the course of this lecture. But even before you start to do the refactoring, there are certain things that need to be considered seriously. The first one is you should know why you are refactoring. Uh, are you doing it because it is necessary for some reason? Any of the 4 or 5 reasons that I mentioned before? And also, even before you get started, you should know where do you want the code to end up being after you've finished with refactoring, because one of the things that happens, and I don't know whether that happens to anybody else or not, but it happens to me all the time, that when I start looking at a code that I wrote, say, 6 months ago, and I'm looking at it and I'm going, why did I do this? Why is this written so badly? And I want to change the whole thing. And before I know it, I've messed it around to the point where I don't have a working code anymore. So it helps to have very focused idea of how much and how far do you want to change the code before you start to refactor it. So to answer these two questions in the context of the heat example that we're working with, why do we want to refactor? We want to refactor because we are working with a monolithic code so that there is no reusability in any part of the code. And that in turn makes it difficult to devise tests, and there is no extensibility in the code. So to answer the second question, where do we want to be after refactoring? The answer to that question is closer to the second version, which means a modular code, which is into well encapsulated units, so that it is more maintainable and extensible. Then the second thing that I mentioned was to know the scope of refactoring. So what does it mean to know the scope of refactoring? And that goes down to being very clear about how deep a change should be happening, which parts of the code you want to leave completely untouched, and also having a good, decent idea of how much of the code is going to be affected. So again, to answer those questions in context of the heat example that we're working with, is that we are not looking for any capability extension here. We do not have any performance considerations. All that we want is a cleaner, more maintainable code. And so how are we going to affect the code? We are going to separate out the utilities and generalize the interfaces. We will move the global definitions out from the one big chunk of code into a header file. We want to create a general build function, but we are not, and this is the important thing to know upfront. In this example, we are not writing any new code or making intrusive changes to any of the code, which means that there is going to be minimal change made to the actual body of the functions that we have sitting around in the code. We are only making surface level changes to the code in order to do this refactoring. Then the next step in refactoring before getting starting is to know the cost estimates, and that is a real challenge, because people are notoriously optimistic when it comes to expecting in terms of figuring out the amount of time that it is going to take to change a code, because in your head you seem to know how much change is going to be needing, and then you sit down and you get your hands dirty with the code, and you find that one thing leads to another, and before you know, you're working with a lot more change than you originally started out with. So knowing your cost estimate is important, and it is also equally important to assume that it is probably going to be on the optimistic side. And then you should be, so because you have a working code, you actually have a way of building up your verification regime before you get started. And it is absolutely important to leverage that and be ready with that um, as you are as you start to alter the code. So what you do is you check for coverage provided by the existing tests, similar to the kinds of coverage that David Rogers talked about in the testing module. It's also very important to identify gaps. By gaps, I mean is that you should do this mental exercise of thinking through that if I touched this part of the code and I made change to this part of the code, do I have a test which can pinpoint if I made a mistake in that transition? So those kinds of gaps you should develop tests for before you get started. You should make tests at various granularity, and full scaffolding is always useful thing to have. And you should also absolutely make sure that there are very demanding integration and system level tests, because you want to be unit tests. In refactoring, depending upon unit tests is a sure shot, on only unit test is a sure shot way of ensuring failure. So you should, because interoperability is an equally critical thing to verify for coverage. So for making sure that there is no regression happening. So it's very important to have demanding integration and system level tests. And then what happened here? Okay. Also, because anytime you change the code, and we are working with machine precision, the digital floating point numbers usually in scientific code, you should always know the bounds of what is the acceptable behavior change. Because, so first of all, acceptable behavior change, not just in terms of the floating point numbers you're generating, but also in terms of convergence behavior, the stability behavior, if you're making any changes to the algorithm as you are doing the refactoring. And also error bounds, because bitwise reproduction of results is very unlikely to happen after transition. So in your head, you should have a map from here to there in your refactoring process. And the other important thing to keep in mind is that when you're doing your cost estimate, you should totally incorporate the overheads of testing into the refactoring cost estimate. That includes not just the overheads of developing new tests, but also the overheads of having to run these tests on a regular basis, ideally on multiple platforms, because it has been our experience that different compilers have different level of tolerances for bad code. And so if you run it on multiple platforms, again, the chances are that fewer defects are leaking through. So the exercise that I'm leaving to you guys to do yourself is convert heatall.c to a cleaner version with reusable code. So during that exercise, you should think about how you want your final product and go through the exercise of refactoring. It need not look like the solution that is there in the repository. In fact, it would be better if you did not look at that solution before you started to work with the code and came up with your own solution, and then did the exercise and looked through the current solution, so that your thinking is not influenced by the way the code is organized, and that you actually go through the process of refactoring with a small enough code so that you get the hang of the process, the methodology itself. But I'm going to work on a smaller example here, walk through the example step by step. And this example is that I'm taking the clean solution and generalizing it. So currently, the way the code is written is that there is you can select the integration method that you are using at runtime by providing an argument. But the flip side of that is that each one of the integration methods has its own interface. And if you wanted to add another integration method, you would actually have to modify the file heat.c because all of the integration methods are implemented there. What I want to do in this particular exercise in refactoring is I want to generalize update solution interface and break apart heat.c so that in future, I should not have to touch any of the source code, that is any of the C code, in order to add an integration method. And I'm going to do this by changing the build system for achieving that goal. So for the purpose of this exercise, we will use FTCS and Upwind 15 as the two methods of integration that we are going to provide as alternative options. So those are the only two we're working on, not completely, but we want to make sure that all of the methods of integration still continue to work. So this is the first step, and here is a screenshot of what I'm doing. So what I want to do is, first step is that I want to run, do the check coverage and generate baselines for myself. So I run heat with the run name of FTCS results, which means that I want to use the FTCS as the integration method. So with that, I generate the code coverage, and here is the code coverage report, where the what this code coverage report is saying is that the return update solution upwind 15 and update solution crank n were not exercised in this particular instance of running the code. So in order to do this, this is the only change I have made so far in the make file, is that I've added a flag dash coverage. Okay, so, but because we want to be making sure that we have baselines for both update solution FTCS and upwind 15, in order to, this is all we need to do. We just want to exercise the call to upwind 15. And so we run heat algorithm with upwind 15 and present a different run name for it, so that now we have two directories. FTCS results contains the solution from the FTCS integrator, and upwind result has solutions for the upwind integrator. And so with that, now we have the necessary baselines, and we have made sure that the code is coverage for the instances that we are trying to exercise in this instance. So the starting code, if you look into the solution, looks like this, is that we have the definitions of these three functions. And so the important thing to note is that between these three functions, the interfaces are not identical. The update solution crank n has an extra argument, and it also has an extra step in initialization. And so if we want to have a uniform interface, because in future we may want to also change, we may also want to exercise update solution crank n, so we have to take that interface, the difference, into account. So what we do is we generalize the interface, where if you notice, we make it look, because the third one, the update crank n, has its interface is a unification of these two interfaces. We have generated an interface now that combines both the arguments that were needed by the first two as well as the third, and then we modify the make file. So now in the make file, we have three different objects defined, and those objects are actually making use of different functions. So now those functions have been broken up into different files. Each one has its own implementation of an integrator. And these are the changes that we have created into the make file to be able to just build the make with one only. So, and we also add a null implementation for initialize crank in FTCS and Upwind 15 so that this particular interface here this part looks the same for all of the codes. And with that, we have now a single, the code has been refactored. There is a single interface update solution instead of different interfaces for each of the integrators. And now what we do is, we run the, we build the first instance by specifying the integrator we want to use. We do the second interface, we verify that we run it with the integrator we want to use, and then we verify both of them against the baseline. And if the results match, then we have effectively done the integration. So to take a recap here, this refactoring process was to make sure that we wanted to add extensibility into the code, and the trade-off was that we were now going to be we will have to pick the specific integrator we are using at compile time instead of runtime. So that's the refactoring we have done, and these particular steps took care of making that refactoring happen. So that was a simple toy example to highlight the steps that are necessary without overloading information. The next thing that I want to do is I want to actually work through a real world example. So FlashX is a multi-physics, multi-component, multi-several things code that is also used by several domains, including several science domains such as astrophysics, laser plasma, fluid structure interactions, etc., etc., etc. And it does that because it has a infrastructure that has extensibility built into it, and capabilities can be added into it in a sort of plug and play way. So this original structure came into existence at the turn of the century, somewhere around 2000, 2001. And it was designed for the distributed memory parallel model. And now it needs to undergo a fundamental change to be able to work on heterogeneous architectures. However, I am not going to, so it is a bigger project than I can cover in just 1 hour of lecture, but there is one aspect of this refactoring that I'm going to talk about at great length in this talk today. And this is that so Flash is an AMR code. The adaptive mesh refinement was provided by Paramesh, which is an octree AMR. An octree AMR, basically what you have is the individual sections of the domain are organized logically in the form of an octree, where there are clear parent-child relationship between blocks at finer granularity and coarser granularity. Paramesh was no longer supported, and so we were looking for a different AMR package, and turns out that AMRX was a good choice. Now, AMRX is a fundamentally different block structured AMR in the sense that AMRX says we can have a finer block sitting anywhere inside of a coarser section of the domain, as long as it is fully encased within that section of the domain. So our job, but all of the physics that is built for Flash assumes that it is going to be relying upon an octree-like AMR. And so our job was not only to bring in the new AMR package, but also to make it mimic the behavior of Paramesh so that all of the physics in Flash will not break down because the behavior of AMRX is different from that of the physics. So this is the goal we are working with, replace Paramesh with AMRX, which means that a few things that we can say straight away is that the scope of this particular refactoring is largely changing in the grid unit at this level and below. It should be largely invisible to things that are happening at the levels outside of the grid API, which means that physics shouldn't be fundamentally changing in order for this to work. So the first thing that we have to do is we have to make a plan for getting there from here. An important aspect of refactoring is on ramping, because when you're making changes to a code as complex as this, you want the changes to be incremental, because if you made a wholesale change to any part of the code, good luck with verifying that it is still correct. So then the design part is making sure that the API is appropriately modified, the ways in which grid interacts with the physics unit. All of the physics units themselves have a wrapper layer that is meant for interaction with the grid. That part of the interface needs to be modified. And so what are the intermediate steps that we want to have? What are the intermediate goals that we want to reach? And finally, realizing the goal of the change. So this gives, and I'm going to go into details of all of these various stages that are shown here in this figure. So don't spend too much energy looking at it now. But the considerations that we worked with is the cost estimation in terms of expected developer time. That is the people who are going to be working and actually doing the changes to the code, including the design and implementation. The other thing that we had to worry about was extent of disruption in the production schedules, because this is a live code. People are using it for running their science. And therefore, there were going to be, in transitioning from one format to another, there was going to be disruptions in production schedule. And therefore, it is important to get a buy-in from the stakeholders, in the sense that all of the people should be on board, because this is non-trivial amount of change. It is going to take a large enough time that everyone should be on board with the change. And that includes the users, for not just the time that it would take to develop, which means the time that this code is going to be available, but also in terms of disruption to their science runs and production runs that they are going to do. So we followed our own rules of thumb that I've outlined before. And we said we made an initial estimate at 6 to 12 months. In the end, it turned out to be closer to 12 months. And but at the end of it, we did have this part working out. So now I want to go through steps in the process. So we started out with Flash, and so the new code is now called Flash X. It's no longer Flash, but we started out with Flash version 4.4. The first thing we did was requirements gathering so actually the very first thing we did was, in order to exercise AMR, we needed to have at least one physics unit that we could exercise and work with. And so instead of using a fully functional shock hydrodynamics, what we did was we first created a simple hydrodynamics code that we could generate results from and create the baselines, or the golden files, as David Rogers put, and have them as something that we could compare against as we modified the code. So this was the very first step, creation of a simple hydrodynamics module, which basically hid most of the mathematical complexity that goes into shock hydrodynamics, but still generated results that could be that would change if we had made a mistake in the interface with the grid. Then we did the requirements gathering for AMRX mesh, in terms of how does the interaction between AMRX and the physics that it supports differ from the interaction that Paramesh does with the physics that it differs. The biggest difference turned out to be that Flash was, when using Paramesh, because paramesh is also written in Fortran 90, it was simply looping over blocks through a simple do loop. Whereas AMRX, written in C++, actually creates iterators that the codes use. And for the reasons that go beyond just changing over to AMRX, but also for the other features and capabilities that we wanted to bring into FlashX, ultimately, we realized that the iterators are better option because a lot of the details of infrastructure can be hidden from the physics if you're working with iterators. And so fortunately, Fortran 90 also provides a way of having iterators. So the first thing that we did was we realized from this requirement gathering that, that we needed to have we needed to build iterators instead of looping over blocks to get the simple hydro to work. So that's the next thing we did as a result of that requirement gathering. We changed. We didn't yet bring in AMRX. We're still just working with simple hydro and paramesh. But the next stage of change was that we built in iterators in the grid interface between the hydro and paramesh. The next step was we looked at how the grid API needed to be augmented and changed in order to accommodate those iterators over paramesh. So the iterator sat over paramesh, and for AMRX, we provided a new alternative implementation. So in Flash parlance, what you can do is you have all of these various units that encode and encapsulate a particular functionality. Because it's component based, what you can have is you can have multiple alternative implementations of the same functionality that the configuration tool is able to pick at the time that the application is being configured. And so it was already possible in the pre-existing Flash to have two different versions of the mesh. One was a uniform mesh grid, and one was an adaptive mesh refinement paramesh. So now we included another new alternative implementation of the grid API that sat over AMRX mesh, and we made sure that this API worked with AMRX and exercised that in purely uniform grid mode, so that we could do it in steps, in small steps, incremental steps, which are very important in the refactoring process. So the first stage of completing this work after the iterators were done and the new alternative implementation was done was to have to run both paramesh and AMRX in purely uniform grid mode, therefore not exercise any of the more complex AMR machinery, and make sure that we were getting consistent results, because in this way we could make sure that the grid structure produced between AMRX and paramesh was identical, and therefore there were not likely to be too many differences in the results generated, and we could work with a relatively stringent tolerance and make sure that this thing is working fine. The second step was when we started to exercise actually the AMR functionality between the paramesh and hydro. So of course we had to update our comparison utility so that they could do the comparison of mesh generated by AMR versus hydro. But here we did an interesting intermediate step. Because we have these multiple alternative implementations, what we would do was to make sure that they were working with identical meshes, because AMRX has its own refinement criterion and its own generation of meshes, and it doesn't guarantee that the same refinement pattern will be generated even if you apply the same refinement criterion. What we did was we initialized using paramesh, generated the mesh from paramesh, copied over the metadata of the generated mesh from paramesh into the AMRX metadata so that AMRX thought that it had generated the mesh and let the physics run with the AMRX interfaces. So this is a little bit complex, and I want to make sure that I'm clarifying it, is that what we are doing here is we are simultaneously running paramesh as well as AMRX, but we generate the mesh using paramesh, make AMRX believe that it has generated the mesh, that the mesh is native to it, and that it is that it is running with paramesh. And so this way, again, we could get it down to the point where we should have bitwise identical results generated between running with paramesh and running with AMR. Notice that in all of this time, we are still just working with a simple hydro. So the next step then is bringing in a complex hydrodynamics, the actual solver that we need to work with, and make sure that the same behavior that we just exercised in the previous step of the mesh generated by paramesh, the mesh handed over to AMRX, and AMRX made to believe that it generated that mesh, and then letting it run the simulation as though it has been in charge always, and producing the output and making sure that the generated data is all right between the two of them. Then in the next step, we had to enable the AMRX features of both the packages, which means that things like flux correction at the fine coarse boundaries and regridding, etc., etc. Along the side, of course, what I haven't mentioned, but what was going on all along this was the fact that there were unit tests being developed in all of these stages for individually exercising the various capabilities that we were enabling within AMRX mesh also. So the unit tests came into existence for guard cell fill, for flux correction, for regridding, for any of the basic functionalities that being exercised for AMRX with the grid unit interface. So then in this stage, the third stage, as you can see, that we enabled the fine coarse interactions, which means the flux correction, and we made sure that the top level interaction between the hydro driver and the AMRX mesh was implemented. So here again, we still kept the ability to make AMRX think that it generated the data out of paramesh, that it generated the mesh that was brought out of paramesh. And the reason why we are doing all of this in this particular way is because our gold standard for regression testing have been long exercised with paramesh, and therefore we had greater confidence in the results generated by paramesh. And in this case, we were making sure that all of the interfaces that we were doing with the AMRX were actually working out all right. And then in the final stage, what we had was a new grid implementation as an alternative implementation to paramesh using AMRX. And then we got all of the other bits of physics that we needed to be. So now that grid had been exercised, the next final stage was then bringing in other physics units from old Flash and making them work with the new interface that we had for the grid unit. So this is just one part of the process. As I said, this process has been going on, but the things to take away from this were that the most important thing here that we had to think about was our on-ramp strategy, which was which means that we really had to break down the change in structure to the point where we could make changes in small steps, bit by bit, And this planning of the process was actually a much more challenging task than doing the implementations themselves. So the takeaways from this particular exercise that I just outlined was that when we are having, when we are doing the refactoring, we have to have, in order to have a good outcome, we need to have why are we doing it? We have to know how much refactoring do we want to know? We have to know the cost. We have to make a plan, step-by-step plan in great details, have a very strong testing and verification regime already built in, and also finally to get a buy-in from the stakeholders. And so this was all I had for for this particular presentation, and I think I'm quite a bit early, so there's plenty of time for questions.
And there's a lot to ask questions about. That's a very
it's a very dense
presentation. Yeah,
yes.
It's very detailed. But I hope people found it a useful example, real world complex software refactoring.
So I've got a quick question. This is really interesting. After your initial planning phase, there was the next phase has your grid API, and that grid API, you guys developed that during the planning phase after looking at all the requirements, right? That didn't already exist inside Flash?
Well, one grid API did already exist inside Flash. Wait, let me go back to screen sharing.
And then, so you guys adapted that grid API
yes.
to meet the requirements from both. And then it seems like was that the hard part, basically?
No, that wasn't the hard part. So
okay. They were similar enough.
See, so right here, if you see the picture, there is the grid API. And this grid API was already, it already had things like, give me the pointer to the block of data, do the flux correction at this point, or because what we did was we put all of the state data under the control of grid. So all of the physics is like a client that asks for data and it gets it and operates on. It doesn't want to know under the hood how the data and the discretization is being managed, right? So yes, what we found was, and it wasn't so much for the AMRX, but also the fact that we wanted to change from looping over blocks to actually using iterators is why the grid API needed to change. So yes, we adapted that, and that changed to reflect the fact that now all of the physics, which also meant that even though we had intended not to be intrusive to any part of the physics at all, we couldn't get away with it completely because it's the wrapper layer of the physics. So up from the point below where the physics is operating on a block, we still didn't have to touch anything. But above that, in the sense of how the blocks were obtained and how the relevant accompanying data like dx's and dt's, et cetera, that are needed to do the computation were obtained, that part of the wrapper layers in the physics unit also had to change.
Oh, okay.
But we kept it at that level. Yeah, that's right. But your question was if that was the hardest part. No, that wasn't the hardest part. The hardest part was devising the ramp on. Because if you notice, we went through quite a few contortions in the steps for making the transition, because upfront we realized that if we started to do this in a way where we started with Paramesh and then we had the AMRX ready and we wanted to compare them, that this was going to be a lost cause, right? So those contortions were the hardest part to devise. And then someone's asking, Isaac, did some of the modules break because they needed an octree structure? Actually, no, they didn't. So the basic fundamental difference that turned out to be that we had to deal with was the fact that AMRX operates, its internal data structures are all organized, assuming that you operate on one level at a time. Whereas octrees just care about being given the block. They don't care about which level they are on. They really don't. And the reason why you have to respect that when you're working with AMRX is that there is the things like the flux registers, the data structures that reconcile the fine structure with the coarse structure actually sit between levels. And so you cannot completely do away with working on the level structures. And that's the part that we had to deal with in terms of the higher level interface in the physics, in terms of how would we iterate over blocks, because when you're doing, say for example, when you're doing hydrodynamics, there are three steps to it. The first step is actually computing the fluxes. The second step is doing the update, and the third step is reconciling the fluxes and adjusting the updates on the at the fine coarse boundaries. And so there is a global communication involved in there. And that's the part which we had to restructure, the part where you basically do the reconciliation between fine coarse boundaries. And your other part of the question, whether there are Fourier transforms involved. So in any case, you cannot do Fourier transforms directly on AMR. You have to do things to them. And those machineries are completely separate for both Paramesh and AMRX. Those are internal to the two packages, and the physics doesn't know about it.
I have questions for Anshu. Don't be afraid to unmute and go ahead and ask. We have time, or you can type them in the chat if you're a little shy.
So in this particular part of refactoring, there were 3 of us, and none of us full-time.
And it took how long to get to the end of
It
this part?
took, like I said, it was closer to 12 months. So keep in mind, when I say 3 people, I am mostly just participating in the design and the discussions. I wasn't doing any of the coding. So the actually people coding, 50% of one FTE and another full-time FTE. That's it.
That kind of makes me wonder, did you have to deal with updates coming in from the development team adding new features while you were doing the refactor?
Fortunately, so this was, I made a misjudgment. There was one particular section of this that I had thought about including and I didn't, but that is an important portion, is that there are 2 ways in which you can do a deep refactoring like this. In this instance, we realized that the changes ultimately are going to be deep enough that we are not going to do an in-place change, which means that we are not touching the current production code, and we are building the framework from scratch, and then we are migrating physics into the framework one by one. And so people who need more physics will have a longer wait time before they can get to using FlashX. People who need fewer physics can already use it. But yeah, so the methodology that we followed was that we first built the infrastructure to our satisfaction, the framework to our satisfaction, and didn't try to make the changes in place. Okay, so the question from Sagar Bhatt is, what other considerations did you have to make considering this supposed to run on hybrid hardware? How did you account for the communication and making sure right parts of the code run on the right hardware? that is a completely different story, and I did not touch upon that at all. So that part has actually turned into a research project in its own right. It is not just a refactoring project because Flash is a Fortran code, which means that C++ template metaprogramming based performance portability solutions aren't open to us. And therefore, what has been going on is that we have been, as I said, effectively deconstructing tools like Cocos and Raja in terms of smaller, less intelligent chain of tools that together provide the same functionality as Cocos and Raja as a whole do. So what we are doing, and I'll be happy to talk about it offline and even later today if you like, but that's what we are building is a complete orchestration system. And in that orchestration system, there are three components. There is a key value dictionary that actually mimics the behavior of template metaprogramming in terms of being able to express the same code with to express code for multiple devices using a single source with specializations happening in the form of definitions of the keys. Then we have a domain-specific runtime that just manages data movement between devices. And then we have a very simple, again, a domain-specific code transformer that takes in what we call the recipe for a time stepping method and converts it into a driver with appropriate mixing of APIs. So it's a very complex system that we've been working on now for 3 years. And we are still mostly not in production with that.